Welcome to Lab 4. In Lab 4 we are going to focus on the oscillations of a spring. In this lab we're going to try to model a spring that is moving in an arc side to side while oscillating. So the only two forces that we are going to observe in this lab is the gravitational force and spring force. We're neglecting any other forces such as air resistance. The formulas we're going to use for updating the position and then plotting the spring is first we need to get the gravity force and the spring force. We know that gravity is just mass times little g, which is 9.8, and that's in the y direction only, negatively pointing down. Then also we have F spring force, which is going to be S, which is the relaxed length, minus the length it's stretched to, times K, which is the spring constant, times the unit vector. So this will means whichever the force is along the spring pointing towards its stationary point. So our F net in this lab is only going to be F grav and F spring. So to update the position, we use Newton's second law, which is the final velocity equals the initial velocity plus F net divided by the mass times the change in time. And since the force is not constant, we can say that velocity average is equivalent to velocity final. So when we're updating the position, we know that R final equals R initial plus the average, which is the final velocity, times the change in time. We then implement these equations into our code, as you can quickly see here. And these we use F grav, F spring, and their combination to give us F net, and use this to update the ball's velocity and position. After running this code, we get this graph. And this is just as we predicted, because the blue arrow, which is the force of the spring, is always pointing along the spring up to its attachment point. And this is because the force by the spring is the spring constant K times S, which is the L0, which is the relaxed length minus the stretched length, in the direction, the unit vector of the spring. So the spring force will always be pointing up it. And then the black arrow here is F grav, and this is going to stay the same size and always point down. This is because force of gravity equals mass times little g, and since the mass of the ball is not changing and little g is 9.8 and that's a constant, the magnitude of the force will not change. And since gravity is always down in the negative y direction pointing towards the earth, the arrow remains pointing down. Next, we are going to focus on the energy in our system. As stated earlier, in this lab, we are making our system include the earth and the spring. Thus, the change in energy must be zero because there's no outside transfer in our system. Everything is happening within. We know that the kinetic energy is 1/2 m times v squared, where velocity is the velocity of the mass on the end of the spring moving. Then we know the potential energy of the spring is equal to 1/2 k times s squared, where k is the spring constant and s is the length it's stretched to minus the relaxed length. Further, we know that the potential energy of gravity is the mass of the ball times g times the ball's position and y from its starting point. Thus, we know that delta E must equal these three things added together, and delta E must be 0. So once we run the code and graph these four things, we know that the blue, which is kinetic, red is going to be our potential of gravity, green is our potential of spring, and as you can see, yellow, which is delta E, remains 0 and goes along the x-axis the entire way. So that means there is no external forces acting on our system, that there's no change of energy either in our system. All that when the potential energy and the kinetic energy of these three things are added together, we will always get 0. So when the spring is as compressed as it can be, we know that the potential energy of the spring will be at its highest, thus the potential energy of gravity will be at its lowest, and vice versa. So after running this data, we've got a graph of our model versus our observation. The red line is our observation and the blue is this model. I think the model and observation match up pretty well. The only difference might be in observation when I was using tracker, where I started the clip might have been a little off because I said the velocity was 0 at that point where it started, but it was very hard to pinpoint exactly when it was dropped, and this could have an influence almost throughout of how they match up because they're just barely offset the whole way. Now for a quick discussion about the what does it mean questions. The first question was the energy principle satisfied? And I said yes, because as we showed earlier, the change in energy in our system was 0 throughout, and that's because our system included the earth and the spring. And then also the next question was, for oscillation periods, should we use the Y position or the X position? How do these differ? I used the Y position in this lab, and that's because when he pulled the spring to the side, he didn't change the Y position very much off of the relaxed length compared to L. But in the X position, we don't know exactly how far he pulled it off, so that's going to affect the period. So therefore the Y, tracking the Y position is a better use for calculating the period and thus the spring constant.